All right, rock stars, we are back on our calculus adventure. This is actually take 2 on this video. I did the full recording, upload, and then I actually taught the lesson the next day and decided that I was a much better teacher than I was YouTuber, and I found a bunch of mistakes that I wanted to do over, so I reworked the lesson. I think it's much better now. So if you watch the old one and you want to watch the new one, cool. There's some subtle differences and some obvious ones, but hopefully this is much more clear. This is our second to last video, second to last lesson in topic 2. And actually, you're really done with your derivative rules. We should know all of our trig derivatives and natural log and log and all that fun stuff. So I like days 23 and 24 to kind of connect or do an overview on everything. And really, day 24 is just going to circle all the way back around to our first lesson for this topic. Day 23 is going to touch a little bit more on the application. So what I'd like you to do, please, is tackle this opener that's here. It's asking you to solve 5 questions, evaluate 5 expressions based on the 2 graphs on the right. And if you're watching this video, you can see the graphs in color. They probably aren't in color on your paper because, well, I'm a teacher and I don't print things in color. So good luck, and then once you're done, unpause and we'll see how you did. It's okay if you get stuck. Just try each one. Okay, so we should be back, and let's take a peek at how we did. Whenever we're evaluating a composition of functions, we always need to start with the inside piece, so we're just going to leave f of something, and we'll tackle g of 4. We're going to go to the graph of g, we'll go to an x value of 4, and we'll say g of 4 is 1. Very exciting. And then we got the 1 from over here, and now we have to do f of 1, so of course we'll have to go to the graph that is f. And f of 1, I think, is 1 right here. Cool. We might as well do g of 1. Skip down here, and then we can go back to the other derivatives. So same thing as before. We'll first do g of 1, work that inside function. And I think we go to 1, and then we say, where's g? Well, g is at -1 at x equals 1. Then we need to evaluate g of -1. So we need to go to -1, go to g, and we end up getting +1. Very cool. Now we have these derivatives. Well, we need to remember that derivatives measure the slope or the steepness of a graph. And luckily these are lines. Lines have really easy steepness to measure. If these graphs were curvy, it might be a little more challenging. So let's take a look at f prime of 2. F prime of 2 means go to the x-axis at 2, go to the graph that is f, and let's just put a point here. Okay, well, if they had asked us for f of 2, then they would, of course, want the y value that corresponds to the input, and the y value would be 0.5. But they didn't. They asked very specifically for f prime of 2. So they want to know, at this point and this point alone, how steep is it? What is the slope? Well, this point is resting on a line, and the benefit of that is any point that's resting on this line will have the same steepness. It doesn't matter where you're standing, whether you're looking down the line from here or down the line from here or up if you wanted to look backwards. It's all the same steepness, and that is one of the properties of a line. A line has a consistent slope, right? That's why an equation 4x minus 3 has a slope of 4, because everywhere on the line it has a steepness of 4. So, if you want to know the steepness or the slope or the derivative at this point, let's just find the slope of this line. And you could do, of course, your y2 minus y1 sort of thing, but why not just count? We have a graph here. Rise is down 1, run is over 2. I think my slope is -1/2. Easy enough. So f prime of 2 is -1/2. Now, particularly, really that is measuring the slope at this single point, but because it's a line, it's actually measuring the slope of the line. Let's look at 2 more. G prime of 4. All right, G prime of 4. Let's erase this, see a little bit more room over here. G prime of 4, we need to go to the graph of G at 4, and we need to measure the steepness of that specific point, but again, it's a line. How about rise over run here? Looks like G prime of 4 is going to be 2 over 1, which is just 2. Okay, and then last but not least, G prime of 3. Well, G prime of 3 is certainly right here. I'll just keep that in red, why not? And that presents a bit of an issue, I think. The issue with G prime of 3 is on the left side we have a line segment with a slope of 0. Should have done that in green. Let's switch it up. That has a slope of 0. However, on the right side of this, we have this part that we just found the slope of, and this line had a slope of 2. So the question becomes, does this point, this vertex, this sharp point, this cusp, if you will, does this have a slope of 2 or a slope of 0? Which line segment does it belong to? Both? Neither? And the answer is, it doesn't really belong to either because it's not squarely in the middle of one or the other. In fact, we say that g prime of 3 does not exist. And that's due to the fact that on either side of that point, or even infinitely close to that point, there are two very different slopes. The slopes never end up agreeing. And in fact, we can even, of course, bring this back to limits. This is why it's a nice 1-2 lesson to end with. Tomorrow I'll do some limits as well. We can say that the limit as we approach 3 from the left side, that's the piece that I did in green up there, I'll just circle it so we know it's green, of the derivatives of all the slopes on this line segment are not equal to the limit as we approach 3 from the other side of that line segment. And, I mean, we could even be specific about it. What is the limit of the derivatives? What is the limit of the slopes of that line? Well, they're all 0, 0, 0, 0, 0, 0, which means they're just approaching 0. Versus the yellow one, we're approaching that point, and I think for the yellow one, they are all approaching positive 2. Right? Easy enough there. So, what do we do with that? Well, we actually need to define a new vocabulary word. When the limits of the slopes does not agree at a specific x value, we say that that function is not differentiable. Differentiable. Oof, I'll probably misspell that word at least twice today. At that point. In fact, to be differentiable at a point, a function either has to have a slope at that point, or you can say it has to have a derivative which exists at that point. Now, there are actually several ways that you can determine if a function's not differentiable. And one of the easiest ways is just visually using a graph. So let's go ahead and experiment down below. There are two functions very, very similar to each other. One is the absolute value of x minus 1, and the other is, in parentheses, x minus 1 squared. One is linear absolute value. It should make a V-shaped graph. You might even want to put a plus 0 so you can see that vertex there. And then the other is a quadratic, also in HK or vertex form. So pause the video, try to graph each of these, and then actually, if you're feeling particularly bold, try to fill out 1A and 1B down below each graph. Ready, set, go. Alright, so you should have these graphs done. Just as a friendly reminder, the vertex at each is going to be right at 1, 0, right? We do the opposite of h, k, 1, 0. However, the differences are much more stark after that. We can see that this one will go one way, and then I'll switch colors, and it'll go the other way like so, versus our parabola is going to, let's see, up 1 over 1, up 3 over 1, right, something like this. Doesn't have to be perfect, doesn't really matter. Okay, so there are my two graphs. Now, the question becomes, are these graphs differentiable everywhere? Well, on the absolute value graph, I'm pretty positive the absolute value is differentiable everywhere except maybe at one point. And the reason that I know it's differentiable everywhere is because this absolute value, this linear absolute value, is made up of lines, and lines have slope everywhere, right? This line has a slope right here. In particular, it has a slope of down 1 over 1. This line has a slope over here. It has a slope of up 1 over 1. So any point that you pick on this graph has a slope, which means any point on that graph is differentiable, except maybe at x equals 1. I'm not sure if at x equals 1, if our graph is differentiable. Okay, well, let's go ahead and look at this parabola over here. This parabola, to me, I think is also probably differentiable everywhere except maybe at x equals 1. And that's easy enough to see. If I put a point on here, you're like, well, I can't really measure the slope. And you're right, it is very tricky to measure the slope right there. However, ask yourself, could you draw a tangent line that bounces off the parabola right there? Sure. And what's the slope of that tangent line? Well, the slope of the tangent line, I don't know it exactly, but it's clearly negative, right? You can maybe argue it's like down 2 over 1 or something, right? It's not perfect, but you can definitely draw a tangent line there. And if you can draw a tangent line, that means that your graph has a slope, because a tangent line has the same slope as the graph it's tangent to. And if a graph has a slope, it has a derivative at that point. So it seems to me that both of these graphs are differentiable everywhere except maybe, again, at x equals 1. Not sure about that. Well, let's go ahead and evaluate the limit of the slopes at x equals 1 for each graph. For our absolute value equation, we're going to go through and just set up two limits here. And you're going to have to write kind of small, sorry about this. We are going to look and see if the limit as x approaches, oh, my dog decided to bring in a squeaky toy. That's mine now, you lose. If you can see the limit as x approaches 1 from the left side of our graph that we're calling f of x, but we don't care about the y values. The y values approach 0 on each side. No, you can't have that back, that's mine. Get your own squeaky toy. So instead, we want to put this little prime right here, yeah? And we want to make sure that what we're talking about then are the slopes of the graph, because the slopes are what determine differentiability. And then we'll say, well, are those slopes equal? And sometimes you'll see a little question mark over the equal sign because we're not really sure here. Are those slopes equal to the limit as we approach 1 from the right side of f prime of x? Well, hopefully you're saying, no, they're clearly not, because this slope is down 1 over 1. This slope is over 1 up 1. So we have a slope of negative 1, which is clearly not equal to a slope of positive 1. What that means then is because the limit of these slopes aren't equal, exactly at 1, f prime of 1 means at 1, exactly there is no slope. So in this case, we would say that f prime of 1 does not exist because the limit as x approaches 1, just 1 this time, of f prime of x, that means from 1 from both sides, does not exist. Yeah, so if that two-sided, or if those one-sided limits don't agree, if the two-sided limit doesn't exist, then our slope doesn't exist at a point, and we say our graph is not differentiable at x equals 1. Let's compare that to the parabola. Parabola-wise, let's get rid of this tangent line here. This gets a little bit trickier. It says evaluate the limit of the slopes at x equals 1. So I guess it probably should say as x approaches 1, but that's fine. We won't mesh words here. So let's go ahead and look at the limit as x approaches 1 from the left side, and I'll do this side in black over here, of g prime this time. So g prime of x, and we want to see, is that equal to the limit as x approaches 1 from the positive side of g prime of x? Now, on the absolute value graph, we could actually measure the slopes. We're like, cool, we can count the slopes. Here, it's a little harder, but I postulate we can actually find an answer, and we're going to do it by looking at tangent lines. So I actually have this ready and graphed for us. So I'm going to go ahead and create this parabola. And what I've also done is I've built a program, not really a program, I built an equation that causes the tangent line to sit on this parabola no matter where I move it. So I'm actually going to go ahead and move the tangent line to the left a little bit. Right, and I actually went a little bit too far there. We can see the point of tangency up here. Because there's a tangent line, the graph has a slope at that point. Right, and in particular, because the tangent line is going down, the parabola has a negative slope or a negative derivative. So if I drag this a little bit over, take a look at what happens, right? Still have a tangent line, still have a tangent line, still have a tangent, still negative slope, negative slope, negative slope, negative slope. But what's happening right about here? Right, as I get really close, what's happening to the slope? Well, the slope is still negative, but you'll notice that it's not as negative, it's more shallow. So maybe at the beginning the slope was like negative 10, it was really steep, and then now we're at negative 5. And then right now, right here, I bet we're at a slope of like negative 1/2 or negative 1/4. What are our slopes approaching? Well, I bet if I move it just right at 1, what is that slope? Well, that's a slope of 0. So on the left side of this parabola, we had slopes that eventually approached 0. Was that the same thing on the right side? Well, if I start over here, we have a positive sloped line. It's going up, 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 but now it's still going up, but take a look at this, right here. that is still a positively sloped line, but not by much. This one's less than up 1 over 1. This might be like up 1 over 2, right? It's a slope of a half. That's not a very big slope. And as I approach 1, as I stop right at 1, which might be easier said than done, did it? You'll notice the slope is 0. So I actually argue that in this case of the parabola, the slopes here approach 0 from both sides. They start very negative on the left, but eventually end up getting to 0. And on the right, they start very positive, but eventually end up getting to 0. And so 0 equals 0, and what we're going to say here is that g prime of 1 equals that limit that we found over there. It equals 0 because the limit as x approached 1 of the slopes of the graph equaled 0. Now, again, we talked about doing this maybe visually. So if you had to explain the difference between these two graphs to a friend, let's say a friend that's maybe only 5 or 6 years old, a young sibling, or a sibling of a friend, something like that, how would you visually explain the differences of these two graphs? You can't say one's a parabola, one's an absolute value. A 5-year-old would know that. What visually is the main difference between this vertex and this vertex? They're both vertices, but what's the difference? Well, hopefully you said something along the lines of, well, the one over here kind of has like a sharp point, and the one over here is pretty smooth. And that really is the visual difference. If you can identify a sharp point on a graph, then you can be pretty confident that that point is not differentiable. The reason it's a sharp point is because you have two slopes coming in that aren't getting closer to each other. They're at odds with each other, so they meet at a sharp point. Versus if you can find smooth spots on a curve, you're probably more convinced that that is a point that is differentiable. Now, how do you justify that on an AP exam? Well, in the past, it's really been kind of up in the air. I've collected a set of responses that AP readers have accepted in the past, with the caveat of they might not accept them in the future. And in fact, in the past, some of these they haven't accepted on some exams and they have on the other. So you can take a quick read through. I don't need to read all of them, but there's a couple good ones that stand out. I hear a cusp a lot for a sharp point. No distinct tangent line, I think, is a really clever way. And again, we're trying to justify something being not differentiable. So we're talking about this absolute value. So what does it mean for there to not be a tangent line? Well, not being a tangent line, and actually it might be easier if I just drew a new graph. What if I drew the graph that looks like this? And I'm going to really, that's very often called a cusp of a graph. Well, look at all these tangent lines we have. We have a tangent line here. Okay, we could draw another tangent line that comes over here. There's nothing wrong with that. We could draw another tangent, whoopsies, if I could learn how to erase, that'd be exciting. We could draw another tangent line that's even steeper. But if I wanted to draw a tangent line right at that point, wouldn't the tangent line be going vertically? And I think that'd be a no-no. Because a vertical tangent line has no slope. And if something has no slope, or an undefined slope, then it has no derivative, it's not differentiable. And also, please note that we could not put the tangent line right here, because then clearly the tangent line does not have the same slope as that pointy point right there. And I put a little emphasis on pointy point because at some point in the past, some graders decided that pointy point was an acceptable way to describe the part of a graph that was not differentiable. Do not use pointy point. You will not get points in my class for a pointy point, but it is kind of fun to say. Now, the reason that I'm making a big show about these words is because look at the ones that the readers haven't accepted. They haven't accepted because there's a vertex, and that to me makes sense. I mean, this is a vertex, but this is also a vertex. So you can't say a vertex is not differentiable because on the parabola it is and the absolute value it isn't. But they also haven't accepted peak or jagged edge comes to a point, not differentiable. That's silly. Explain why a function's not differentiable. Well, it's not differentiable because the graph is not differentiable. Well, okay, that does not work. Not smooth. They didn't even accept no slope, which is interesting because I've said that a few times. So we should notice then that there's no real rhyme or reason as to what AP seems to accept. And so to guarantee a correct full point response, we're not going to use any of those words. We're going to use one-sided limits, just like what we did up above. So for any of the problems down below, even if you get a graph, please don't discuss the sharpness of the graph, but instead do your best to bring it back to the one-sided limits of the derivative. Now, what happens if you're given an equation that you don't know how to graph, or you're just like, I don't want to graph that? Are there other ways to determine a lack of differentiability? And yeah, there are. I mean, we just spent this entire unit using derivatives. We should probably know something about them. So for example, let's examine the graph of f of x equals x to the 1/3. And I'm actually going to show you the graph first. You should know what this graph looks like, but I'll let you off the hook if you don't. It's our cube root graph, right? It's that kind of S-shaped graph. It's actually a pretty good S right here, yeah. Looking at this graph visually, it's actually very smooth and pretty, right? Tangent lines all the way through, very smooth, pretty graph. Don't have to pick up my pencil. I think there are no sharp edges, no jagged points, no pointy points on here. So does that mean then it's differentiable everywhere? Well, let's check derivatives. Derivatives give a great idea of differentiability. So let's take the derivative of f of x equals x to the 1/3. Gives us f prime of x equals 1/3 x, subtract 1 from the power to the negative 2/3. Becomes 1/3 times 1 over x to the 2/3. Or even going a step further, 1 over 3 times, this is going to be the cube root of x squared. Any of those are fine for the derivative. I'm going to use the last one. I think it looks the cleanest to me, but it's up to you. Well, if something is not differentiable, it means there is not a derivative at that x value. And if there's no derivative, it means something broke that derivative equation. So looking at this derivative equation, can you think of what would break a fraction? Well, hopefully you said, oh yeah, it's when you divide by 0 in a fraction, you get a DNE, the world explodes, calculator doesn't let you do it. You know, one of those easy, casual things. And I bet even further, you could look at the denominator and say, well, what does x have to be to turn the denominator to 0? Hopefully you can see that x has to be 0. And so, when x equals 0, f prime of x does not exist. And what that means then, so I'll even say, therefore, f of x, the original graph, is not differentiable. I'm going to do DIFF mostly because I've run out of room, but that's also a very common abbreviation, at x equals 0. But how come we couldn't see that from the graph? Well, I think actually now that you know that 0 is the place where it's not differentiable, that you actually probably can see that from the graph. And why, or what's happening there? Well, you might have noticed the graph seems to go vertical there, straight up and down. So think about tangent lines again. We have a tangent line here, positive slope, steeper tangent line now, right? Close to maybe an up 1 over 1, and then an even more steep tangent line. And by the time we get to 0, what does the tangent line look like? Well, it's going infinitely up. It has an infinitely large slope. It's going straight up and down. Can you picture that vertical line that's tangent here? A vertical line has no slope, or an undefined slope, which means that the graph to which it's tangent also has an undefined slope. And if you have an undefined slope, you are not differentiable. Okay, well, let's look at one more. Let's look at a graph with a removable discontinuity. And I didn't give you an equation here, but we could expand it to an equation if you want. So I'm going to go ahead, and actually we don't need that much space. I'm going to go ahead and just graph the equation y equals x. That's an easy equation. It's one that we should know, right? Y equals x. We know that it has a slope of 1 everywhere. I can even do a couple tick marks and we'll pretend that this is accurate, though it won't be. We go up 1 over 1. I am going to put a removable discontinuity right here, though, and then we're going to do something like this. Okay, so we're assuming that this graph goes straight forever. There's my removable discontinuity. Okay, well, the question becomes, is this graph differentiable at x equals 2? Well, let's check everything we've done so far. First, we might want to look at the limits. I mean, well, if you do the regular limit, clearly we're approaching 2 on the y-axis, but I really mean the limit of the slopes. Well, notice that this piece of the line has a slope of 1. It's up 1 over 1. It's y equals x. And this piece of the line also has a slope of 1. It's up 1 over 1. So if we look at the limits of the two slopes as we get close to that hole, the limit of the slopes exists, right? So right here we could even say the limit as x approaches 2 from both sides of y prime of the slopes is 1. So does that mean that this is differentiable? Well, no, it is not differentiable, because we're talking about differentiability at a point. which means the point itself contains some amount of slope, some amount of steepness. If there's no point there, it cannot contain slope. The absence of a point can't have any characteristics. So this point has no slope, or rather there is no point, so it cannot have slope, and so this graph is not differentiable at x equals 2, and we could even say a because. You have a couple options. You could say because the graph is not continuous. You could say because x equals 2 is not defined. You could say x equals 2 does not exist, something like that. Now, let's go ahead and put all of this together. We have a couple conclusions to get, and we're really going to work backwards with this. So let's start with the one we just did. If a function is not continuous at a point, right, if there's no point there or the limits don't meet up or something, then the graph is automatically not differentiable there. It's a really quick, easy thing to check. You're like, okay, is this equation differentiable? You're like, let's check continuity first. Nope, not continuous. Nope, not differentiable. Cool. If a function is continuous, then f of x might be differentiable. For example, we have two continuous functions on this page, right? Our parabola is differentiable. Our absolute value linear function is not differentiable, right? They are differentiable everywhere. They're both, this one's just not differentiable at 1, and this one, the parabola, is differentiable everywhere. Last but not least, if f of x is differentiable, so if someone says, let f be a differentiable function, then you know one thing for sure. You know that function is also continuous, right? And that is because of our not statement up here. If you get a not, then two statements that don't have the not are going to be true, right? If f is differentiable, then f is continuous. Okay? So how do we actually determine if f is differentiable at a point and prove it mathematically, besides looking at a graph and going pointy point? Well, there's two steps here. And the two steps, one of them we already know, and that's actually why I really like this lesson, because we learned this in topic 1, and now we're circling back to it to make sure you don't forget. We want to make sure that the function is continuous at that point, differentiable at a point. Whoopsies. And I'm going to use the point x equals c. So how do we determine if a function is continuous at c? Well, first, f of c has to be defined, which really just means the point exists. Right? The second thing is we need to make sure that the limit as x approaches c of f of x exists. There has to be a limit there. Usually if it's piecewise, you will use one-sided limits to show that. And then last but not least, we have to make sure that the point is in the same spot as the limit. That should be review. What's new? Well, step 2 is determine if the derivative at x equals c exists. And the way we do that is we use one-sided limits to show that the limit as x approaches c of f prime of x exists. So it's just like continuity. It just has one more criterion that we have to show. Now, I do make a brief note here, and I think it's important, especially for the practice problems that will follow. Don't show every single step every single time. If you do that, you're going to hate your life over the next 8 problems, and this shouldn't be too terrible. What you really want to do is just quickly check all of these in your head until you come to a step that doesn't hold true, right? If you plug in a point and you're like, in your head and you're like, okay, there's a point there, but then you plug in the point to each branch of the piecewise equations and they're not equal, then you're like, oh, wait, we know it's not continuous. Don't do this step then, right? Don't do this step. Stop right there, because they're going to say, is this differentiable? And if you can show that one of these steps breaks, then just say, not differentiable because, and just do the work for that one step. Okay, so I'm actually going to go the long way around for this problem, and then I'm going to give you the faster way to do it. Now, really, these are all practice problems, and if you want to skip through the rest of these and do them on your own, that's fine. Check your answers at the end, but I do want to really kind of put into practice what I just mentioned. So, is this piecewise function below differentiable at the given value of x equals a? Justify your answer. Now, you might be tempted to look at this and say, oh, I'm pretty good at graphing. Why don't we just graph that? Well, I actually have it ready to be graphed for you right here. I have this function. I'm going to zoom out slightly. And we're looking at this, and you're like, well, whoa. I see where these meet. I see that this is x equals 3. Is that a sharp point? And then you start to second guess. You're like, well, honestly, it doesn't look super sharp. It kind of actually looks a little smooth. And the more you look at it, you're like, maybe it's not a sharp point at all. Maybe it is. You're a little suspect, but you're not positive, which is why we don't actually use a graph to justify. Instead, we're going to go through our steps. Now, again, I'm going to go the long way around. I would suggest you don't write anything till the very end because I'm going to erase it all and then show the fast way. But the long way is going to take like a couple minutes. So what's the long way? Well, if this is going to be differentiable at x equals 3, then the first thing I'm going to check is the continuity. And I'll label that over here just in case you want to see it. Continuity, we have a couple things to check. First, I want to make sure that f of 3 exists. Well, f of 3, that's this equation down here because there's an equal to, becomes 3 times 3 minus 5, 9 minus 5, which is 4. Cool, f of 3 exists. The second thing I want to check is, does the limit as x approaches 3 exist? And the way that we check that, I would suggest that you be a little bit more careful than normal on this. It's better to be picky with your notation now to build good habits than be sloppy. So what I mean is, I don't want to say the limit as x approaches 3 from the left side of, and actually let's do it the right way and then I'll explain the wrong way after. So the limit as x approaches 3 from the left side of f of x equals the limit as x approaches 3 from the right side of f of x. That's what I should show. And then from here, we're going to replace f of x with the actual branch that's in charge. So from the left side, that's x squared minus 5. And from the right side, I think that's going to be 3x minus 5. Okay. And then let's just plug in 3 and be done with it. 3 squared is 9, 9 minus 5 is 4, and over here, 9 minus 5 is 4. The one thing I see a lot of students do is they skip this first step. They say, meh, I'm not going to do that. I'm just going to skip right to the step. There's still limits there. That's cool. But then the issue is, after this, they are going to show their last step, and their last step I'll do down below over here. They're going to say, you know, f of 3 equals the limit as x approaches 3 of f of x, which all equals 4. And they're like, look, I showed all of this. And I'm like, wait, where did you show the limit was 4? And they're like, well, right here, obviously. I'm like, well, how do I know that's talking about f of x? You never said the limit was f of x there. So I think it's a very important first step to make sure that you actually bring in the limit that you're trying to prove at the end. If you're talking about the limit as you approach 3 of f of x, then talk about the one-sided limits of f of x to begin. So we showed that this function is continuous, right? We can maybe even say like, therefore, continuous at x equals 3. Cool, we're champions. But we're not quite done yet, because all continuity tells us is that these two pieces come together. And that's what we saw on the graph. They come together, but we don't know at what angle. We want them to come together perfectly smoothly, so now we need to move on to step 2. Okay, well, how do we do step 2? Well, we first probably need the function for the derivative. And that might seem intimidating, but it's actually easier than you think. We just need to take the derivative of each of the pieces here. At this point, this should be pretty straightforward. The derivative of x squared minus 5 is 2x for x less than 3. And the derivative of 3x minus 5 is just 3 for x just greater than 3. I'm going to leave that equal sign off. And in fact, we have to leave the equal sign off here because we don't know if the slope is actually 3 when x is equal to 3. That's what we're trying to prove right now. We're trying to say, is there a slope at 3? We're not sure. Well, to actually verify, now let's do that differentiability part. Differentiability. Sure, crushed it. All right, well, we're going to do the same thing as before. We need to guarantee or verify that the limit as we approach 3 from the left side of f prime of x is equal to the limit as we approach 3 from the right side of f prime of x. Well, what function is in control from the left side for the derivatives of f prime? That's 2x. And the right side, that is 3. 2 times 3 gives us 6, and 3 just gives us 3. 6 equals 3. Well, that is clearly not true. Because these derivatives are not equal as we approach 3, then we would say, therefore, not differentiable at x equals 3. Now, I told you it'd take about 5 minutes. There's a lot of work here. You're like, do I have to show all this work for every problem? No, definitely not. Because this wasn't differentiable, we only needed to show the part that broke differentiability. So how do we do that quickly? Well, I'm going to start over. I'm going to leave my differentiability piece there because I will probably need that at the end. But I think all of this becomes irrelevant. Now, by the way, if it did end up being differentiable, then you would need all the work. We'd have to prove everything there. But if it's not differentiable, here's how I'd approach this problem. Like differentiability. Okay, let's check continuity first. And in my head, I just make sure there's an equal sign. There's an equal sign, point exists. Cool. Second thing I'd check, are the limits equal? And I just, in my head, plug in 3, right? We get 9, we get 4, we get 4. Cool. Therefore, it's continuous. I just proved in my head it's continuous. I'm not writing any of that down. I have my fingers crossed that it's not going to be differentiable. Most of these end up not being differentiable. So why would I want to write something that's irrelevant? It doesn't matter if it's continuous, if it's not differentiable. So let's get to our next part. And the next part is this part that I did here. I had to take the derivative, show the limits, and then we'd say not differentiable at x equals 3. I should probably go a step further. I'd say because the limit as we approach 3 from both sides of f prime of x does not exist. It doesn't matter that it's continuous there. They just said, is it differentiable? It's not, and that's the only reason it's not. Who cares about the continuity? So as you go through the rest of these problems, be careful. Do as much work in your head as you can and just write the important part, because again, most of these are not going to be differentiable. So go ahead and pause me, try the next 2 pages, there's 2 pages left, and then unpause and you can come back together if you need any help. All right, and hopefully we are back. Let's get to it. And I'll take you through my thinking and then write what needs to be written. So if f is the function defined below, then f prime of negative 1 is what? Well, f prime of negative 1 all depends on the derivative, and I will tell you this problem has been on tests in the past, and here's what students do. Students take the derivative, and then they say, well, that's 3, that's negative 2x, and then they do x less than negative 1, and then they make the big faux pas. They say greater than or equal to negative 1. And they're like, cool, to find the derivative, I just do f prime of negative 1. That's this bottom equation, negative 2 times negative 1, that's 2. Ha, f prime of negative 1 is 2. And they don't go through the full process. We are, at least mental math-wise, going to go through the full process. So, continuity first. Are we continuous? Negative 1 in here, 5 minus 3 is 2. Negative 1 in here, 3 minus 1 is 2. Yes, both the limits are the same. There's an equals. Yes, it's continuous. Cool. We just crushed that. Second part, limit of the derivatives. Well, I got this. If I plug negative 1 in here and I plug negative 1 in here, do we get the same answer? No. The top branch is 3 and the bottom branch is 2. Uh-oh. I know this is not differentiable. There should not be an equal sign here. So how do I explain this? Well, first, we need to actually put into algebraic symbols what it means to be plugging both of these in. And we're not finding f prime of negative 1 twice. No, we're finding the limits, right? We're finding the limit as x approaches negative 1 from the left side of f prime, and we're seeing if that's equal to the limit as x approaches negative 1 from the right side, because there are no equal signs here yet. We can't actually be at negative 1. And then we would say, well, this one becomes 3, right? This one becomes negative 2 times negative 1, and those are not equal. So my conclusion, f prime of negative 1 does not exist because the limit as x approaches negative 1 of f prime of x does not exist. Again, not too bad. We can fit the work in here that's necessary. 3. F is defined below. Explain why, although the limit of f prime exists at 0, f prime does not exist. And so what this is saying, and I'm going to erase this, so be careful, they're saying if you take the derivative here, we get 3x squared, and in the bottom piece we get 3x squared plus 0, or just 3x squared. Clearly those functions are the same. So if you were to take the derivative of these functions, well, then they would both be 0. So the limit as we approach 0 of f prime of x does equal 0, but that's not enough for differentiability. And so I'm actually not going to write this. It's good to see, but we're going to save some space here because we haven't checked continuity yet. Well, there's an equal sign, so the point exists. We plug in 0 here, that's 0. Plug in 0 here, that's 1. Wait, 1, 0, 1 is 1? Uh-oh. That's no good for continuity. What we're really checking here is we're checking the limit as we approach 0 from the left side of f of x, not f prime here, and the limit as we approach 0 from the right side of f of x. Okay, so as we approach 0 from the left side, x cubed is in charge. As we approach 0 from the right side, x cubed plus 1 is in charge. This is 0, and this is 1. And so we can say that f prime of 0 does not exist because f of x is not continuous at x equals 0. Right? No continuity means no differentiability. No differentiability means no derivative at that point. You could even go further and you could say, well, because the one-sided limits aren't equal, that means this is a jump discontinuity. If you wanted to look at the graph to see that jump discontinuity, I do have that one prepared for you as well. We have these two pieces right here. There's your jump discontinuity, right? From the left side you approach 0, from the right side you approach 1. There cannot be a slope where our limits are at two different pieces. Okay, well, let's finish off the rest of this then. We just have a couple left here. 4 and 5 are very similar and very common problems. You might see these as a multiple choice question. They are giving us another piecewise, a bunch of piecewise today, and they're saying, okay, f is defined below, and we want to make it differentiable. We want to not only make this parabola intersect with this line, we want them to intersect seamlessly, flawlessly, at a smooth curve. We want there to be a slope at 2. Well, how does this work? These two, you do need a bit of work, unfortunately. So you're either going to want to write small or you're going to want to use a different piece of paper because we're going to try to use good notation here. Well, the first thing that's got to happen is that these two pieces have to be equal. But we can't just set them equal because we need to relate it either to continuity or the limit of the derivatives. So by plugging 2 into these, what are we really doing? We're really looking at the limits here. So we're saying the limit as x approaches 2 from the left side of f of x does have to be equal to the limit as x approaches 2 from the right side of f of x. Continuing down, we're going to replace f of x with our 2x squared from the left. Yep. And we're going to replace f of x with our ax plus b from the right. And then we evaluate 2. 2 times 2 is 4. 4 times 2 is 8. 8 equals 2a plus b. Well, that's actually going to be useful eventually, but it's not useful to us yet because we have two unknowns. You can't actually solve to figure out what one of them equals. There's actually, I think, an infinite number of combinations, right? If a was 4, b would be 0. If a is 0, b would be 8. If a is 2, b would be 4, right? There's an infinite number of combinations, and all those combinations are doing is causing the parabola and the line to be in the same place. But it doesn't tell us what angle they're running into each other. That angle, of course, is dependent on the derivatives. So we should probably do that limit of the derivatives thing. Derivative of each piece, 2x squared, 2 times 2 is 4, so we get 4x, for x is less than 2. And then ax plus b can be tricky, so let's just pick a line. What if we had 5x plus 7? Well, the derivative of that is just the slope of it. It's just 5, the number multiplying by x. So the derivative of this is just a. All right, and then we want to say x is greater than 2. Well, how does this help us? We need the limit of the derivatives. So we want to find the limit as x approaches 2 from the left side of f prime, and make sure that that's equal to the limit as x approaches 2 from the right side of f prime. Well, what function's in control from the left side? Well, that is, of course, 4x. And from the right side, that is just the constant a. 2 times 4 is 8. We can't even plug 2 in over here because there's no x value. So I think this just becomes a. Oh, look at that. We found that a is 8. That's so exciting. But we're not done yet because they asked for a and b. So where do we go? But back to where we began. We need our other equation over here. But now, lucky us, we know that a is 8. And so I think we are going to be able to work this out. 8 equals 16 plus b. Subtracting 16, I think, gets us b is negative 8. And now we have found the two values that not only make the two pieces of the function run into each other, but at a nice, smooth, happy curve. Okay, going through the rest of these a little bit faster now. We need to, again, pretty much do the same thing here. We're going to find f prime. That becomes negative 2x. And this becomes m. X greater than 1. I'll do the differentiability first. Why not? The left side has to be equal to the right side. Looking a-okay. The left side is negative 2x. The right side is m. We get negative 2 equals m. Gosh, we're good. Already found m, yay us. Well, then we get the limit part. This can go away, we're done with that. So we want the limit as x approaches 1 from the left side of f of x better be equal to the limit as x approaches 1 from the right side of f of x. The function that's in control from the left side is 4 minus x squared. The one that's in control from the right side is that mx plus b. Actually, we know m. Let's just replace m with negative 2x plus b. Easy enough. Should be lowercase. Whoopsies. And then we plug values in. So we get 4 minus 1, which is 3, and then we get negative 2 plus b, so I think that tells us that b is 5. Gosh, we're good. Moving on down. Let the function be defined below. Which of the following statements about f are true? Justify your answers. Well, looking at these limits, and I'll work sideways for space here, the limit as x approaches 1 from the left side of f of x is the function 3x minus 2. That is a creepy looking 3, not a fan of that. And we're trying to make sure that that's equal to the limit as x approaches 1 from the right side, which is controlled by the natural log, everyone's favorite, of 3x minus 2. Well, substituting in, 3 minus 1 is 3, minus 2 is 1, and then over here it becomes the natural log of 1. Are those equal? Well, I don't think so, because any log of 1 is 0. So these are not equal, which is true, not that guy. If that's not true, that means that our limit as x approaches 1 from both sides doesn't exist. That means our function is not continuous. If it's not continuous, we automatically know it's not differentiable. So we're done with 3. Go us. What about 2, though? We can still have limits of slopes exist, even if it's not differentiable. So I think we should probably find f prime of x up here. 3x minus 2 just becomes 3. 3x minus 2 becomes 1 over 3x minus 2 times the derivative of the inside. It's times 3, isn't it? Yeah, don't forget that chain rule. So when we want these limits over here, we'll switch colors. The limit as x approaches 1 from the left side will be controlled by the constant 3, but as we approach 1 from the right side, it's controlled by 3 divided by 3x minus 2. So I think that's going to give us 3 on the left. Plugging 1 in here gives me 3 over 3 times 1 is 3 minus 2 is 1. It gives me 3 equals 3. So actually, this is true. And that's a pretty tricky problem right there. I bet a lot of people would realize the first one isn't true and maybe assume everything else isn't, but we do need to check those. Not differentiable, but the limit of the derivatives does still exist. Alright, 7. Which of the following statements about f must be true? Justify your answers. Well, if we know the limit as x approaches a of x equals f of a, isn't that essentially the definition of continuity, right? For continuity, we need the point to exist, the limit to exist, and then to be equal. So that's continuity right there. F is continuous, x equals a, yes. Is f differentiable? Not necessarily, right? Imagine we had some sort of graph here. I could draw this thing that's happening, and I could draw it like that. There's a sharp point. The limit exists. This is continuous, but not differentiable. So this one doesn't have to be true. The rest of these are kind of interesting. This one says, for all values of x, f of x has to equal f of a. F of a is, of course, a constant. That is a y value. So they're basically saying y has to equal a constant. Well, a constant graph is a graph that looks like this. It's a horizontal line. Nowhere does this mean it has to be a horizontal line, right? It can be any sort of graph. So no, the y values do not have to be equal to a constant. If this is true, does the tangent line have to be y equals f of a? Again, have to be a constant, have to be a horizontal line there? No, of course not. I mean, imagine again, if I had the line y equals x right here, and this is, let's say, a comma f of a, right, the tangent line to this would not be like that. That doesn't make any sense. So it could be, but no. And then last but not least, does the line x equals a, looks like this, is there a vertical asymptote there because of this? Well, no, that only has to do with continuity. So I think a is our only answer that is true. Moving through. All right, another one of these. Okay, what are the values of a and b for which f is differentiable? We got this at this point. Hopefully you've been doing this on your own and you're just checking your work now. Let's find f prime of x. Why not? It's been easier that way. It's just going to be 1 because the b goes to 0, and this is going to be 2ax for x greater than 1, for x less than 1. Let's look at the limits here. The limit as we approach 1 from the left side of f prime has to be equal to the right side. Okay, nothing too bad. And the function that's in control of the left side is certainly 1. The function that's in control of the right side is the kind of weirder 2ax. This just becomes 1. The right side, we put 1 in for x. 2a times 1 is just 2a. And now we can just solve, right? Divide by 2, we get a is 1/2. Does that eliminate anything? A is b plus 1. That could still happen. No such values. We found a value for a. And all the rest are really still in the play here. So let's go ahead and move to our other one. And the other one is finding the limit of the original function. So as we approach 1 from the left side of f of x, is that equal to the limit as x approaches 1 from the right side of f of x? Well, the left side is that x plus b equation. So that one's in control. My handwriting gets sloppy the further we go down, but I don't think you need it to be perfect for this part. Ax squared. Substitute in 1, we get 1 plus b equals a times 1 squared. That's just a, isn't it? 1 plus b equals a, but wait, we know a, right? That's where they got this piece. They were trying to trick you. We know it's going to be 1 plus b equals 1/2. Subtract the 1, half minus 1 is negative 1/2. And we have our two answers, and it is, again, a. 2 problems to go. This one came from a free response quite some time ago, probably over a decade ago now. I bet it even came from the early 2000s when you were all wee babes, but that's okay. We have a continuous function that's defined on an interval. Graph of f consists of a line segment, right? We see the line segment here, and we also see a curve over here, of course. The curve is tangent to the x-axis at 3, so horizontal tangent, there's a slope of 0 there. And on the interval 0 to 6, the function is twice differentiable. So what that means is not including the endpoints, so just skimming over those endpoints and going from here to here, again, not including the endpoints. This function is twice differentiable, which means it has not only slopes or the first derivative exists everywhere, but the second derivative also exists everywhere. It means if you take the derivative, you'll get answers for any value you plug in between 0 and 6, and you'll get answers in the second derivative as well. We don't actually know what the second derivative really does. We won't get that for a while, but either way, they even follow up that the second derivative is greater than 0. That's irrelevant for us. Our only question we need to answer is f differentiable at x equals 0? And then it asks you to use the definition of the derivative with one-sided limits. We're going to alter this a bit. We are just going to use the derivative with one-sided limits to justify. The definition of the derivative is something we'll cover next class. We've seen it before, but we're not going to use it today. Okay, let's start with visuals. Looking at this graph, is it differentiable at 0? Hopefully you said no, and then you didn't yell pointy point. You said the limits of the derivatives aren't equal. However, there is a sharp point there. I'm pretty darn convinced that we are not differentiable at that point. Well, how do we show it? Well, we do the limits of the derivatives. This function is called f, so let's work with that. Let's say we want to find the limit. I said purple. We want to find the limit as x approaches 0 from the left side of f prime, the limit of the derivatives, and compare it to the limit as x approaches 0 from the right side of f prime. Well, the left side isn't bad at all. The left side is a linear function, and we have 2 points. We have this y-intercept here. We go over 1, 2, 3, up 1, 2. So we want a rise of 2, a run of 3. So this is 2/3. But how do we find this derivative over here, it's not a line, it's an ever-changing set of derivatives, right? This point up here is steeper than this point down here, and this point has a slope of 0. So how do we prove that to somebody? Well, really, we just get creative here. We can tell that this derivative, so I'm actually going to say we're going to abuse this a little bit, we're going to say that this is not equal to this limit because, well, what do we know that derivative is at least getting closer to? Well, take a look at this. If I were to put a tangent line here, what is the slope of that tangent line? Well, the slope is decidedly negative. Okay, what if I got closer? What if I put a tangent line right up here? That's like almost right at the point. What's the slope of that tangent line? That tangent line is also negative. In fact, every part of this red graph until we get to 3 has a negative derivative, a negative slope. So all I'm going to say here is that as we approach 0, the slopes are definitely less than 0. And on this side, this is positive, this is 2/3, and 2/3 is definitely not equal to a number that's less than 0. So is f differentiable at 0? Then we would say no, f, always answer the question, f is not differentiable at x equals 0 because the limit as x approaches 0 from both sides of f prime of x does not exist. It's a very clever problem where you actually have to use some good thinking to understand you're not going to find an answer, a numerical answer. You're going to have to bring some logic in and say, well, at least we know it's negative, and a negative is not equal to a positive. Okay, let's finish this off. Just a brief reminder, it's a pretty easy one. 2 of the 3 answer choices below are always true. 1 is not always true, and we just have to decide which is which. Well, A, if f is defined at x equals a, then does the limit as we approach f of x at x equals a equal to f of a? Well, for something to be defined, it means there's a point there. So I'm just going to draw that point really quickly to give our nice counter example. Here's a, here's f of a. They told us f of a is defined or a is defined, so there's a point. But just because there was a point, does that mean the limit has to be in the same spot as the point? I don't think so. I mean, look at this. Okay? There's a limit. It's not in the same spot as the point. Great. I think this is not always true. Probably even be shorter to just say sometimes true. It could be true, right? This limit could be equal to the point, but doesn't have to be. B, if f is continuous at x equals a, then does the limit have to equal the point? Well, I think yes, right? Don't forget your 3 criteria of continuity here. They told us f is continuous, so that means then not only is f of a defined, does f of a exist, and not only does the limit as x approaches a of f of x exist, or is that defined, but also the last part is the limit as x approaches a of f of x equals f of a. I mean, that's in the criteria for continuity, and so if it's continuous, that has to have been true. Last but not least, if f is differentiable at x equals a, then does this have to be true? You're like, well, differentiable, isn't that slope thing? Well, yeah, it is. However, we need to remember that differentiability, crushed it, that differentiability implies continuity. So if a function is differentiable, then it is also continuous. And if a function is continuous, is this true? Why, yes, it is. We just saw that over here. And in fact, that is a big kicker for people on tests. They will generally start sentences like, let f be a differentiable function. And then they might ask you to prove a theorem or do something with continuity. And a big thing students miss on those questions is they just say, because f is continuous. And then you look back at the problem and go, well, it didn't say it's continuous. And so what the AP exam actually requires you to do is if a problem says it's differentiable, but you need to talk about continuity of a function, you need to make a statement that connects, that bridges the gap from differentiability to continuity. And the way you do it is you say something like, as f is differentiable, then it is also continuous. And you need to put that sentence. Many people that I graded last year missed only a single point on their exam, and that single point was because they forgot that one sentence. They used the theorem correctly after that. They did everything else great, but they forgot that one sentence, and so the grader said, well, how do you know it's continuous? Are you just making this jump? Right? Because even though we know that differentiability implies continuity, you haven't shown us that you know that yet. So thank you for sticking around today. I appreciate all your hard work. Hopefully, if you watched both videos, this one's better than the first. I feel much better about it. And yeah, we have one more video to come back to for this topic. So thanks for all your amazing, amazing hard work in this weird 2020 year, and I will virtually see you next class.